Welcome to another deep dive, everybody. Today, we're going to try and answer a pretty fundamental question. How do we even know the universe is expanding? It turns out that light itself is the key to unlocking this mystery. We can use it almost like a cosmic detective's toolkit to understand the universe's past and present.
That's a great way to put it.
Our main source material for this deep dive is excerpts from a cosmology textbook. It's full of mind-bending ideas about how light travels through an ever-expanding universe. We're not just talking about abstract theories here.
Right. We're going to use light, the way it travels, the limitations it has, and the secrets that are encoded within it to piece together a history of the cosmos.
I love that.
It's like using starlight to read the universe's diary.
It really is. So to start unraveling this cosmic mystery, we need to go back to the very foundation. How does light actually travel through an expanding universe? The textbook dives into some complex concepts here, things like space-time intervals and light geodesics.
Yeah, those concepts, they might sound intimidating at first, but they're really just ways to describe the path that light takes through the fabric of spacetime, which itself is expanding.
Okay.
You can imagine if you were to stretch a rubber sheet with a marble rolling across it.
Okay.
The marble's path would curve, of course, because of the sheet's expansion.
Uh-huh.
And much like that, the path of light is influenced by the stretching of space-time.
Okay, so it's kind of like warping the path that the light is actually taking.
Exactly.
That's a helpful visual. And, the textbook author even throws out this thought experiment to kind of illustrate just how vast space is. Think about all the energy that's ever been collected by all the optical telescopes throughout history. That's got to be a mind-boggling amount, right?
It is a truly immense amount of energy. But then think about this, that entire amount of energy is less than what it takes to lift a single book.
Really?
Yeah. It really puts things into perspective. The vastness of the universe, the incredible distances light travels, and the faintness of the signals we're trying to capture.
Yeah. It makes you realize just how sensitive these instruments need to be. And it brings up another question for me. If the universe has a finite age, we talk about the Big Bang and it happened at a certain point in time, does that mean there's a limit to how far back in time we can actually see?
Absolutely. There are boundaries or horizons that limit our view.
Okay.
One of these is the particle horizon. You can think of it as marking the edge of the observable universe. It's determined by the distance that light has had time to travel since the Big Bang.
So a sort of cosmic time limit,
Yeah,
a fence beyond which we can't see.
exactly. The universe is about 13.8 billion years old.
Okay.
So we can only see light that has been traveling for 13.8 billion years or less. Anything beyond that remains hidden from us, at least for now.
But if the universe is expanding, shouldn't we be able to see even farther than that? Because space itself is stretching, so wouldn't those distances increase over time?
That's a great question.
Yeah.
It highlights a really important point.
Yeah.
It's not simply a matter of multiplying the universe's age by the speed of light.
Okay.
We have to factor in the expansion of space itself, which has been stretching those distances continuously over billions of years.
Got it. So the light that we see from very distant galaxies has actually been on this incredible journey through a universe that's been expanding the entire time.
Right.
It's not just a straightforward calculation. It's much more complex.
It's a very complex process to calculate. And to add another layer of complexity, there's also the optical horizon. Remember that early in the universe's history, before hydrogen atoms even formed, space was filled with this dense, hot plasma.
Yeah.
That plasma was opaque to light.
Okay, so light couldn't travel freely, like a thick fog almost.
Exactly. The optical horizon marks the boundary beyond which we can't see because light simply couldn't travel through that early opaque universe. We can only see back to the moment when the universe became transparent, which was roughly 380,000 years after the Big Bang.
Okay, so we have two types of horizons. The particle horizon, which is limited by the age and expansion of the universe, and now the optical horizon, limited by the early universe's opaqueness.
Right.
Are there any other horizons we should be aware of in our cosmic exploration?
Yeah, there's one more that's crucial. It's perhaps the most mind-bending of them all, the event horizon.
Okay.
This horizon marks the boundary beyond which events can never be observed, even if we wait an infinite amount of time.
Whoa. Okay, so a cosmic point of no return.
That's one way to think about it.
Kind of like a black hole's event horizon, but on a universal scale.
Exactly. And this is especially relevant in a universe with accelerated expansion, like ours.
Right.
As space stretches at an increasing rate, It pushes some regions of the universe beyond the point where their light will ever be able to reach us.
Hmm. So even with infinite time, there will always be parts of the universe that remain hidden from us.
It seems that way, yes. Those regions are essentially cut off from us causally, meaning that we can never interact with them. We can never even know for sure what's happening there. It's like
Wow.
a whole other realm of the cosmos hidden beyond our reach.
A lot to process.
It is.
This is definitely a lot to process. But before we get lost in this vastness, we've been talking about these horizons, but how are these horizons visualized?
Right.
I've heard of these things called conformal diagrams. They
Yes.
sound pretty complex.
They might sound complex, but they're actually incredibly useful tools for understanding the causal structure of spacetime. Think of them as maps of the universe that preserve the angles at which light travels,
Okay.
because the speed of light always remains constant.
So instead of showing like actual distances, they're kind of prioritizing the relationships between events and how light connects them.
Exactly. In a conformal diagram, light always travels at 45-degree angles, so it makes it much easier to see which events can influence each other, which ones are causally disconnected, separated by horizons.
That sounds much more manageable than trying to actually wrap our heads around the actual distances and scales involved here.
It is.
Can you give us an example of how, like, a specific type of universe might be represented in a conformal diagram?
Sure. Imagine a closed universe, one that's finite and curves back on itself like a sphere.
Okay.
In a conformal diagram, this might be depicted as a cylinder, with the top and bottom representing the beginning and end of time.
Okay, I can kind of picture that. So where would the horizons be located in this cylindrical map?
Well, the particle horizon would expand outwards from the bottom of the cylinder as time progresses,
Okay.
showing us the growing region of space that we can actually observe. The event horizon, on the other hand, would shrink inwards from the top,
Okay.
representing the shrinking region of space that can still causally influence us.
So as time goes on, the particle horizon gets bigger, the event horizon gets smaller, and they eventually meet somewhere in the middle of this diagram.
Exactly. And the exact point where they meet, as well as the overall shape of the diagram, depends on the specific properties of that universe, like its curvature and the type of matter and energy it contains.
It sounds like these conformal diagrams can get pretty complex, but they're a really powerful way to visualize these abstract concepts and explore different possibilities for the structure of the universe.
They are. And by studying them, we can gain a deeper understanding of the nature of horizons and how they limit what we can observe, how the universe's expansion shapes our view of the cosmos.
This has been incredible so far, and we've just scratched the surface of how light helps us to understand the universe's expansion. But there's another key piece of the puzzle that we need to explore before we go any further,
Absolutely.
and that is redshift. We're going to dive into what exactly redshift is, why it's such a crucial tool for cosmologists, and how it all ties back to this idea of an expanding universe.
Sounds good.
Welcome back to the deep dive. Before the break, we are delving into the mind-boggling concept of cosmic horizons and how they literally limit our view of the universe.
Right.
But now, we got to explore another key piece of this puzzle, redshift.
Yes.
What exactly is redshift, and how does it help us understand the universe's expansion?
Redshift is fascinating because it acts as both a cosmic clock and a ruler,
Yeah.
helping us measure not only the distances to faraway galaxies, but also how much the universe has expanded since the light we see left those galaxies.
Okay, so it tells us something about both distance and time.
Right.
But what exactly is being shifted?
It all comes down to light waves. As the universe expands, space itself stretches, and the stretching affects the light traveling through it. Imagine you're drawing a wave on a rubber band, and
Yeah.
then you stretch the band.
Oh.
The wave gets longer, its peaks further apart. That's what's happening to light as the universe expands. The wavelengths are getting stretched, shifted towards the redder end of the spectrum.
So that's why it's called redshift.
Yes.
But how does this help us measure distance and time?
Well, the more the light has been stretched, the greater the redshift.
Okay.
And because the universe has been expanding pretty consistently, the farther away a galaxy is, the longer its light has been traveling and experiencing this stretching.
Yeah.
So greater redshift means greater distance.
Makes sense. But you said it's also a cosmic clock, right?
It is. Light travels at a finite speed.
Right.
So when we look at a distant galaxy, we're actually seeing it as it was in the past.
Oh, okay.
The light from that galaxy has been traveling for billions of years to reach us. The amount of redshift tells us how long that journey took revealing how much time has passed since that light was emitted.
Wow. So by measuring redshift, we can peer back in time and see a snapshot of the universe as it was billions of years ago?
Exactly.
That's amazing.
It is. It's like having a time machine that allows us to study the universe's history
That's so cool.
and see how galaxies have evolved over cosmic time.
Yeah, and this is where things get even more interesting, right?
Yeah.
Because redshift doesn't just tell us about the distances and ages of galaxies.
Right.
It also tells us about their composition and evolution.
Exactly. It allows us to study the light in detail.
Okay.
We can analyze the specific wavelengths that are absorbed or emitted by different elements within those galaxies.
So it's like a cosmic fingerprint,
Right.
revealing the chemical makeup of those distant galaxies.
That's a great way to put it. And by studying these fingerprints, we can learn about, the types of stars that were forming in galaxies at different points in the universe's history, how the abundance of elements has changed over time,
Okay.
and even how galaxies themselves have grown and evolved.
That's incredible. So redshift is really the key to unlocking so much information.
Mm.
But you mentioned earlier that there are actually two ways to interpret redshift. Can you explain that a bit more?
Yeah, so one way is what we've been discussing,
Right there.
the stretching of light waves due to the expansion of space itself. The second interpretation, which is still valid, relies on a more familiar concept, the Doppler effect.
Like how the sound of a siren changes pitch
Exactly.
as
Yeah.
an ambulance approaches and then moves away from us.
Exactly. That's a perfect example. The Doppler effect basically tells us that the observed frequency of a wave changes depending on the relative motion between the source and the observer. When a source is moving away from us, the waves are stretched,
Yeah.
resulting in a lower frequency.
Okay.
And in the case of light, that shift towards lower frequencies means a shift towards the red end of the spectrum.
So we can think of redshift as a consequence of distant galaxies moving away from us.
Yeah, and for nearby galaxies, that Doppler interpretation of redshift works pretty well.
Okay.
However, as we look at increasingly distant galaxies, the concept of relative velocity becomes more complex because it's not just the motion of the galaxies themselves that we're dealing with, but also the expansion of space itself that dominates.
So it's like trying to measure the speed of a swimmer in a river that has a really strong current.
It-
The swimmer's own motion is kind of intertwined with this overall flow of the river.
Right. At those vast cosmic distances, the expansion of space itself becomes the dominant factor.
Right.
And that's why cosmologists primarily focus on the interpretation of redshift as a consequence of the stretching of space itself, rather than just the simple Doppler effect.
It's like we're trying to factor in the expansion of the river itself, not just the swimmer.
Exactly.
Yeah.
It's a reminder that our everyday intuition can sometimes break down when we're dealing with the complexities of the cosmos.
Yeah. Now, what about those individual motions of galaxies that you mentioned earlier? Those peculiar velocities.
Right. Galaxies aren't just moving away from each other due to the universe's expansion. They also have their own individual motions within their local environments.
Yeah.
These peculiar velocities are influenced by gravitational interactions with nearby galaxies and clusters of galaxies.
So it's kind of like a cosmic dance, with galaxies swirling around each other while also being carried along by the expanding universe.
Exactly. And these peculiar velocities can also cause redshift or even blue shift, depending on whether a galaxy is moving towards us or away from us within its local group.
Okay, so how do astronomers account for these peculiar velocities when they're trying to measure redshift and determine a galaxy's distance?
It requires careful analysis. Astronomers have to distinguish between the redshift caused by the overall expansion of the universe, which we call the cosmological redshift,
Okay.
and the redshift or blue shift caused by the galaxy's peculiar velocity.
It's kind of like trying to filter out the background noise
Right.
to isolate the specific signal that you're looking for.
Exactly. And by accounting for these peculiar velocities, astronomers can get a more accurate picture of the universe's large-scale structure, how galaxies are distributed within it.
Really is amazing how much information is hidden within the light that we receive from these distant galaxies.
It is.
By carefully analyzing redshift and all of its nuances, we've learned so much about the universe's expansion, the evolution of galaxies, even the mysterious force of dark energy. But we're going to have to save the discussion of dark energy and the specific tests astronomers use for the next part,
Okay.
because we're out of time for this segment.
Sounds good.
Welcome back to our deep dive. We've been on this incredible journey exploring light and redshift. It's amazing how these fundamental concepts can unlock so many secrets about the universe. Before we wrap up, I'm really curious to hear more about those kinematic tests you mentioned earlier.
Yeah.
What exactly are they, and how do they help us probe the universe's expansion history?
Well, kinematic tests, they're like a suite of cosmic experiments. They allow astronomers to really put the universe's expansion to the test by examining how different properties of light change with redshift. We can then compare those observations with various theoretical models, refining our understanding of crucial parameters like the Hubble constant
Right.
and the densities of matter and energy in the universe.
So instead of relying on just one piece of information, like redshift alone, we're kind of combining multiple observations to build this more complete picture of the universe's evolution.
That's exactly it. Think of it as piecing together a giant cosmic jigsaw puzzle. Each kinematic test is providing a different piece of the puzzle.
Okay,
And by combining those pieces, we get a clearer view of the big picture.
I like that. Now, one of the tests you mentioned was the angular diameter redshift relation.
Right.
What's that all about?
It focuses on how the apparent size of an object in the sky, its angular diameter, changes with its redshift. Now, you might assume that the farther away an object is, the smaller it appears.
Yeah, I would think that's pretty intuitive.
You'd think so, but in an expanding universe, it's not always that straightforward.
Wait, so you're saying that things can actually appear bigger the farther away they are?
Yeah.
How does that even work?
It's a consequence of the interplay between distance, time, and the expansion of space. Remember, when we observe a very distant galaxy, we're seeing it as it was billions of years ago.
Right, when the universe was much younger and more compact.
Right, because the light from that galaxy has been traveling for billions of years to reach us, so we're essentially looking back in time.
Exactly, and because the universe was smaller back then, that early galaxy, even though it was physically smaller, might have actually occupied a larger portion of the sky than it does now.
Wow, that's mind-bending. It's like a cosmic zoom lens, allowing us to peer back in time and see these early galaxies in a way that we couldn't otherwise.
It is. By carefully measuring the angular diameters of galaxies at various redshifts, astronomers can actually trace how those sizes have evolved over time, giving us valuable clues about the universe's expansion history.
Fascinating. So we have this angular diameter redshift relation. What are some other kinematic tests that astronomers use?
Well, another important one is the luminosity-redshift relation, which examines how the apparent brightness of objects changes with redshift. This test actually played a crucial role in the discovery of dark energy.
Oh, yes. Dark energy, that mysterious force that's accelerating the universe's expansion. Exactly. Astronomers were studying type Ia supernova, which are often called standard candles because they have a very consistent intrinsic brightness. And what they noticed was that these distant supernovae were dimmer than expected based on their redshifts.
So meaning they were farther away than their redshift would initially suggest.
Precisely. And the only way to reconcile this discrepancy was to introduce the concept of dark energy, this repulsive force that counteracts gravity and causes the universe's expansion to speed up.
So it was through these meticulous observations of light and redshift that astronomers uncovered one of the biggest mysteries in modern cosmology.
It was. And it really speaks to the power of these kinematic tests. They allow us to delve into the fundamental nature of the universe, exploring not just distances and timescales, but the very forces that shape its evolution.
That's incredible. It sounds like we're just getting started, though. Are there any future kinematic tests on the horizon that could revolutionize our understanding even more?
Oh, there are. One really exciting prospect is something called redshift drift. This technique aims to directly measure the change in an object's redshift over time.
So instead of comparing the redshifts of different objects at different distances, we'd be looking for tiny changes in the redshift of a single object over many years.
Exactly. While the effect is incredibly small, it would provide a direct measurement of a universe's acceleration, independent of any specific cosmological model.
It's like trying to detect the faintest heartbeat of the cosmos itself.
It really is. It's a challenging endeavor that requires incredibly precise instruments and long-term observations. But if successful, redshift drift could completely revolutionize our understanding of dark energy, the ultimate fate of the universe.
It's incredible to think about how far we've come in our understanding of the cosmos. From those basic properties of light to these complexities of cosmic horizons and those incredible kinematic tests, it's clear that light is our guide,
Right.
allowing us to unravel the secrets of the universe's vast history and evolution.
Absolutely. It's a testament to human curiosity and ingenuity that we can use something as seemingly simple as light to probe these grand mysteries of the cosmos.
This has been a truly awe-inspiring journey. Thanks for joining us on this deep dive into the fascinating world of light and the expanding universe. Keep looking up and stay curious.